Today's experiment we will be exploring the common ion effect using the equilibrium, the solubility equilibrium of calcium hydroxide as it dissolves into a solution. So we know that for a solubility product equilibrium, that the KSP, the equilibrium constant that governs this reaction, can be calculated in a normal way. We take products over reactants, but the reactant this time is a solid. So the KSP expression for this reaction would be the calcium concentration in the solution total, no matter the source, and the hydroxide concentration squared, the total amount no matter the source. Now, if we are in pure water, we would see that the calcium ion concentration would be expressed as X, and the hydroxide ion concentration would be expressed as 2X. But if we're not in pure water and there's an outside source of a common ion, we would see a different occurrence here. This is known as the common ion effect, where if we have an outside source of hydroxide, so say we try to dissolve calcium hydroxide in a solution that already contains some dissolved sodium hydroxide in it, the additional hydroxide that's present initially by Le Chatelier's principle will drive this reaction to the left. So we'll still have to fill in, if you look at the ice table, we'll still have to fill in some X and some 2X from the equilibrium itself, but the amount of X will diminish because the reaction is going to shift to the left and it's going to diminish the solubility of the calcium hydroxide. So that's the common ion effect. What we're going to do is we're going to go ahead and investigate the common ion effect by calculating the KSP at various concentrations of hydroxide. We should see that the KSP stays constant because the law of mass action states that the KSP is constant. So remember that the KSP has to be the total calcium concentration and the total hydroxide concentration squared. So what we're really interested in is the effect here on X. If the equilibrium is shifted to the left, the amount of calcium generated by the dissolving of the calcium hydroxide should go down. So how are we going to determine that? Well, if you see that in this balanced chemical reaction, whenever we get X amount of calcium, we're going to produce 2X amount of hydroxide. It's going to be twice the amount of hydroxide. So if we measure the amount of hydroxide produced by the dissolving of the calcium hydroxide, then we should know that the calcium concentration will equal 1/2 the hydroxide concentration, where the hydroxide is not the total hydroxide, but the hydroxide that's been provided from this solubility equilibrium. So same is true of the calcium. So the calcium produced by the equilibrium, X, is going to be 1/2 the hydroxide concentration produced by the equilibrium. That makes sense because the hydroxide is going to be 2X. So what we're going to do is we're going to go ahead and measure the hydroxide concentration total in a solution, and then from there we're going to determine how much hydroxide is produced. I'll show you that shortly, how we're going to determine how much hydroxide actually comes from the equilibrium and calculate the calcium. But for a moment, let's consider how we're going to measure the total hydroxide. So we know that hydroxide can react with a strong acid to produce water. This is simply a neutralization reaction. So that's what we're going to do. We're going to take a strong acid, in this case we're going to take hydrochloric acid, and we're going to react it with all of the hydroxide in a solution. So we'll try and dissolve up some calcium hydroxide. The solution can contain some extra hydroxide, and it will also produce some hydroxide by the equilibrium. Those two things will equal the total hydroxide. So the total amount of hydroxide will equal the hydroxide from the equilibrium plus the hydroxide that's provided from the solution itself, the outside common ion. Okay, when we neutralize it with hydrochloric acid, we're going to be measuring the total. Now, the hydrochloric acid we're going to use has this concentration here. So just to remember how we would calculate that then, if we used 10 milliliters of 0.0301 molar hydrochloric acid, and we use that to neutralize 10 milliliters of a solution that contains hydroxide, and the hydroxide is the only thing that reacts with the hydrochloric acid, we should be able to calculate the concentration of the hydroxide. So we know if we take the 10 milliliters of the substance that we know, we're going to use a burette, so we can use 2 decimal places here. Multiply that by the concentration of the hydrochloric acid using units. The concentration can be expressed in millimoles per milliliter. That allows me to not have to switch out of milliliters. That's going to equal the concentration of the sodium or the hydroxide ion that we're neutralizing, because it's a 1-to-1 reaction. We would get the total amount. That's going to be 0.301 millimoles of hydroxide that we've neutralized. And then to get the concentration of that hydroxide, again, this is going to be the total concentration, not just the concentration from the equilibrium. This will be whatever the hydrochloric acid finds in the solution. We would take the millimoles of hydroxide that we neutralized and divide it by the volume of the hydroxide that we neutralized. So if we neutralize 10 milliliters, we're going to use a pipette, so that's also good to 2 decimal places. We would see that the concentrations, of course, would be the same because we used equal volumes. It would be 0.0301 molar for the total hydroxide concentration. So that's how, using a neutralization reaction, that's how we're going to determine the total hydroxide concentration. But that doesn't tell us how we're going to determine then the resulting calcium concentration that went into the solution, because remember, the calcium concentration is not tied to the total hydroxide concentration, but only to the amount of hydroxide that was produced by this equilibrium reaction. So if there's an outside source of hydroxide, we have to take that into account. To perform our calculation then to determine how much calcium was provided by the equilibrium, we would have to organize our data table and understand how everything here is connecting in the data table. So let's say that the calculation that I just did was what I discovered. In run number 2, I discovered a total of 0.301 molar hydroxide ion was found in my solution. In run number 2, what was done was calcium hydroxide was dissolved into a solution that already contained 0.0158 molar hydroxide ion. So that's the hydroxide ion provided by the solution. Okay, the solution was already containing this amount. So how do I determine how much the hydroxide was provided by the equilibrium? So remember, the total comes from 2 sources. It comes from what's already in the solution. Again, the hydrochloric acid doesn't know where the hydroxide comes from. It just neutralizes whatever it sees in the solution. So it comes from the solution itself, and then it also comes from the equilibrium. To determine how much we got from the equilibrium, we would simply subtract. Subtracting the 0.0158 from the 0.0301 will give us the hydroxide that's provided by the equilibrium. So I'm going to subtract the solution from the total, and that should tell me how much calcium hydroxide basically dissolved. The number here would come out to be 0.0143 molar. Now, this came from the equilibrium. So we know the calcium we've already discussed will be provided at half the amount of the hydroxide. To get the calcium then, we would take and divide this number by 2 to get the calcium ion concentration. So we would take 0.0143 and divide that by 2. That gives me a calcium concentration of 0.00715 molar. At this point, probably better to use scientific notation, but anyway, that's what it is. Now, it's really important when you're doing the KSP to remember that you're going to take the calcium concentration times the hydroxide concentration squared, but this hydroxide has to be the total. The KSP doesn't care where the hydroxide comes from. It just knows that it has to manage the same number for whatever calcium ion concentration it finds in the solution and whatever hydroxide ion it finds in the solution. So to solve for the KSP in this example, we would take the calcium concentration and we would multiply it by the total hydroxide concentration, quantity squared. So that would give us 6.4, 6.5 times 10 to the minus 6. Now this is not meant to represent what you will see in terms of your data. Then your numbers might not match that at all. I just threw some numbers out there as a trial to show you how to do the calculation itself. So you'll fill in your own numbers, determining the hydroxide total, and then from there, knowing what our solution concentrations are, and these are the ones that you're going to see. And you should be able to determine the rest of the values and get the KSPs. In the end, you'll take the 4 KSPs and you will report an average of the 4 KSPs. Theoretically, they should be the same because we have to follow the law of mass action. What you should take special note of is the concentration of the calcium, because that's going to describe the solubility, because the calcium ion concentration always equals X. Weighed out about 0.1 gram of calcium hydroxide and put it into 4 labeled Erlenmeyer flasks. The exact amount of calcium hydroxide in each flask is not important. Our goal is that we're going to saturate the solutions and dissolve as much of the calcium hydroxide in each solution as we can. So as long as we've added more than enough to do that, and not too much to make the filtering process difficult, that should be satisfactory. Now, I'm going to now dissolve each of them into the substance in which I have labeled them to be dissolved in. So the first Erlenmeyer flask is to be dissolved in just water. So we're going to add 50 milliliters of water to our first Erlenmeyer flask. Again, the exact amount. Well, you do want to be as careful as possible with this because you do want to saturate it. The exact amount's not that important because the concentration will stay. So we're going to make sure that will dissolve. I'm going to put that aside to look at our next flask. Our next flask is going to be dissolved in the 0.0158 molar solution. So we have our 3 bottles of sodium hydroxide here. So we're going to attempt to dissolve the calcium hydroxide into a solution that already contains some hydroxide ion, our common ion. So, measuring our about 50 milliliters of this solution out. We're not going to use pure water this time, but we'll use 50 milliliters of this solution that already has some hydroxide ions in it. That's the common ion. So there we go. And we'll set that aside. And we're going to try and dissolve it as much as we can. The next one has 0.0 316 molar. So I will find the bottle that has 0.0316 molar sodium hydroxide, and I'm going to add 50 milliliters of that solution into this Erlenmeyer. Now you'll notice that my concentrations are not going to be terribly exact, and you might have noticed in my previous calculation I went ahead and rounded the KSP to 2 sig figs, mostly because even though we are using quantitative glassware for a lot of this experiment, in the end, because of the inexactness of, say, the amounts, the exact concentrations of the graduated cylinder, we're not expecting to be getting better than the 2 sig figs that we'll see at the end. And then the last is the greatest concentration of the sodium hydroxide, so we're going to add the 0.06322, also 50 milliliters of that. Again, to be successful, I should have, to be a little bit more exact, we should have a dry graduated cylinder each time. It's not quite dry, it's a little droplets of water, so they'll be slightly less concentrated than what's indicated on the bottles. That's all right for what we're trying to achieve. So the next thing we'll want to do is swirl these very strongly to try and dissolve as much of the solid as possible. But of course not all of it's going to dissolve because it's a slightly soluble salt, so it's not 100% soluble. And there's common ion present that's going to further suppress the solubility. So they're going to be cloudy. We're not going to try and shake them until they're not cloudy anymore. What we'll do then is, when we're satisfied that we've been aggressive enough with the dissolving process, is we're going to filter out the excess solid remaining, leaving just dissolved calcium hydroxide in the solution with the previous dissolved hydroxide. I'm set up now to filter out the excess calcium hydroxide that didn't dissolve. You can see that it's cloudy here. So what we want to do is capture just the amount of hydroxide that is in the solution right now. So I've set up a filtering station here to filter out the excess calcium hydroxide. So I put my filter paper into 3 of them. I'm going to show you how I've done that here. I fold the filter paper in half, I fold it again, and then I peek out one side like this, put it into the funnel, and wet it down a little bit so that it stays flat. This one's sitting nice and flat anyway, but wet it down a little bit to make sure it stays flat. Now previously I labeled each beaker to show which solution I was filtering in, and then I've carefully lined up the Erlenmeyer flask to make sure that I'm not going to accidentally lose track of which solution is which. So we will pour them in carefully so that that doesn't overflow. And filter through. And we're actually going to do this twice. To make sure that the solutions are clear before we start trying to quantify the amount of hydroxide that is currently dissolved into each solution. So we have to watch, and when I get enough space I'll add a little bit more. And as you can see, gravity filtration just takes a little bit of time. What's nice about this is that I just have to find the concentrations in each one, so it's not super careful in terms of making sure everything's transferred perfectly. I don't have to worry about transferring the solid that remains in the Erlenmeyer flask into the beaker because I don't care about that. I just care about the concentration of the substance that's dissolved in the solution itself. So it doesn't matter. It doesn't matter how much is left behind. So we'll just let those filter through, and I'll actually be filtering it a second time, but I'll do that off camera to make sure that any cloudiness is not in the solutions. Although it's doing a pretty good job this first time, if you can see, you can notice that the solutions are pretty clear. So there's not too much of the solid calcium hydroxide that I can tell that's sneaking through the filter paper. But just to be on the safe side, we will go ahead and filter it through a second time, and I'll do that off camera and also finish this filtering for you off camera because this is about as exciting as it gets. Okay, now we're ready to quantify the dissolved hydroxide that went into our solutions. I've set up a burette here with filled with hydrochloric acid. The hydrochloric acid has the molarity you see here. And I rinsed it 3 times through and then filled it up, but I haven't read it yet. That's your job. And we're ready to go. So I'm going to titrate, first of all, a sample that was dissolved into pure water. So the pure water one is here. Say I labeled it W. And it's still slightly cloudy, as you can see. But I did filter it through twice, so we're going to go ahead and do the analysis. First, we're going to start by pipetting 10 milliliters of our sample into this Erlenmeyer flask. So I have my 10 milliliter pipette here and my pipette bulb. Go. We'll go ahead and put it into the Erlenmeyer flask. So remember, when we quantify, we're going to be quantifying the total hydroxide. Now this is the water. Since the only source of hydroxide was the calcium hydroxide, this will correspond to the hydroxide that was provided by the calcium hydroxide, or the equilibrium calcium hydroxide that you see in the data table. All right, now we have to add some additional water so that we can see our endpoint. Now we're titrating with hydrochloric acid. Since this is now a base solution and we're adding acid to it, we cannot use a phenolphthalein indicator for this titration, so we have to use a different type of indicator. Here is our neutral red indicator that we'll be using. We want it to go through to a red color, but it's going to be colored the entire time. And for indicators that are colored the whole time, seeing the endpoints is often a little bit more difficult. So we'll put a few drops on this, what's called a Kim wipe. It's kind of a tissue that's used for cleaning up glassware and whatnot. And that should be the color that we're looking for when we get to our endpoint. So then we're going to add our drops of indicator, and we see that it's a nice orange color. Now we have no idea where the endpoint's going to be, so we do want to proceed a little bit carefully when we do this titration. So having no idea, we will add a couple of test drops and see what happens. Okay, looks like no indication of a color change. I can see a little bit of red in there, so I'm going to keep adding and see if that red wants to hang around a little bit more. dropwise. Looks like I'm getting some droplets on the sides. Oopsies. So I want to rinse those down, make sure everything's in the solution. Got a little lucky there. Getting a little closer, so I'm going to be a little bit more careful. Whoa! Alright, so that looks pretty good. So we'll go ahead. Let's get you that second reading. Make sure you can read that well. So what I would be doing then is I will have to titrate each one of these twice. And in doing that, I will have a total of 8 titrations that I have to complete. And then you can calculate the KSPs for each one. I'll be doing pictures then of the other beginning and ending points of the rest of the titrations, and you'll then fill in your data table and be able to calculate the KSP for each of these solutions, remembering that for the solutions that already have hydroxide in them, that you have to subtract this concentration from the total to get the equilibrium concentration.